Assalamu alaikum. In this lecture, we'll be discussing about the different losses that are taking place in the transformer, and also we'll be discussing the different tests that are done to determine these losses. And from these tests, we may be also determining the uh, equivalent parameter or equivalent circuit, approximate equivalent circuit of the transformer. So, different losses in the transformer. The first one is the core loss. As we know that core loss is actually the combination of hysteresis and eddy current losses that results from the alternations of the magnetic flux in the core. So the nature and the remedies to reduce these losses, we have already discussed that. We also assume from now on that these losses will be constant because usually we excite the transformer with constant voltage and frequency, and as we have already discussed, these losses are dependent upon the voltage and frequency only. So apart from some construction dependence, we assume that this construction dependence is already fixed, and then they only depend upon the voltage and frequency. And for the ratings perspective, we know that we always excite the transformer on at rated voltage and frequency. We assume that for that purpose that these losses are constant. Now the second loss is the copper loss, that is the loss that is occurring in the winding resistance, and these losses are proportional to the square of the load current. Sometimes we can say only load. The third is the stray load losses. Usually they are very small and they are usually neglected. These losses results due to the leakage flux, and due to that leakage flux that may induce eddy currents in the body of the transformer, or that body is known as the tank, and also in the conductors itself. So these results in the extra power losses, but they are usually very small and we neglect it. The last one is the dielectric loss. These losses take place in the insulating material, particularly in the oil and solid insulations. As I told you, the third and fourth loss, they are usually very small, and for the purpose of ease, we always neglect them. We only take care of the two losses, that is the constant core losses Pi or iron losses, and the variable copper losses, that is PC. So we know that this PC is the combination of, that is we should have in Pi. Pi is the combination of eddy current loss and hysteresis loss. Eddy current loss is given by the equation Ke Bm square F square, where hysteresis loss is given as Kh Bm raised to power 1.6 into F, where 1.6 is the Steeman's constant. Also, we know that the relationship of the input voltage and frequency, number of turns, and the maximum flux is given by this equation. So it is equal to 4.44 F N1 into 5x. 5x can be calculated like this, even, which is almost always equal to V1, whether the transformer is loaded or not. So we can take it as V1 divided by 4.44 F N1. So we convert this into B, because here equation is the B. We just want to replace this B by these equations. So B will be equal to 5x divided by A. Bmax will be equal to 5x divided by A. That means this relation will be now V1 divided by 4.44 F N1 into A. I can replace it by N, just assuming whether this is primary or secondary. Here, if I write it as V1 and N1, it means the primary side. So if I drop this one, it means on the either side, whether it is primary or the secondary. So from now on, we will drop this subscript. We'll always write it as V divided by 4.44 F N A. Now we'll put this equation into this equation, and this equation will get the new equation for the eddy current losses and hysteresis losses. When you put this equation here, Bm square, that means this will be equal to V1 square divided by 4.44 F square N square into A square. Now these three quantities, square quantity, will be in the denominator, and numerator we have F square. This F square and this F square will cancel out. We'll be left with Ke V1 square or V square divided by 4.44 square divided by N square A square. These quantities, as N, A, and these are constant by design. So F square will cancel out. So PE will be equal to some K times V square, by K is these terms, that is this KE divided by 4.44 square M square E square. So this will be only dependent upon the voltage, square of the voltage, eddy currents. Similarly, hysteresis loss, when you put the equation, this equation into this, it will be equal to V1 raised power 1.6, 4.44 raised power 1.6, F raised power 1.6, N raised power 1.6, and A raised power 1.6. So in place of this, when you multiply it by KH and F, we get PH. So F is in the numerator. So it will be equal to, when denominator we have 1.6, when you subtract it, it will be equal to F raised power minus 0.6. P is as it is, V raised power 1.6, and then this K dash will be equal to KH divided by 4.44 raised power 1.6 and into A whole raised power 1.6. So I actually derived the equation in terms of voltage and frequency only. The rest are the constant. In earlier case, it was voltage, frequency, and Vmax. So here we have eliminated the Vmax. We are only left with the voltage and frequency. And we saw that this eddy currents are independent of the frequency, eddy current loss, and hysteresis loss dependent upon both voltage as well as frequency. So total iron loss, this is core loss, Pi should have been here. Please try to correct it. It will be equal to Kv square plus K dash V raised power 1.6 minus into F raised power 0.6. Let us try to do one example. It will be slightly clear to you how to calculate different losses for different values of frequency and voltages. A 220 volt 60 Hz single phase transformer has a hysteresis loss of 340 watt and eddy current loss of 120 watt. If the transformer is now operated at 230 volt and 50 Hz supply, then compute its total core loss. Assume T means constant to be 1.6. That means we are using this formula. So from this equation, we know that PE1 for different voltages, because eddy current loss are independent of the frequency, we have to see if the voltages would have been same, then eddy current would remain the same. But here voltages are different. So let us try to calculate it for the different voltages. Let us say PE2 divided by PE1 will be equal to V2 square by V1 square, where PE2 is proportional to V2 square and PE1 is proportional to V1 square. So PE2 will be equal to PE1 into V2 square by V1 square. So PE1 is given as eddy currents, where are they? 120, that's 120. So V2 is given as the second voltage, that is 230 volt, and V1 is given as 220 volt, that is 220 volt. So when you multiply it, it comes out to be 131.157 watts. Similarly, by using this, sorry, it should have been PH2 divided by PH1. Please try to correct this. PH2 divided by PH1 will be equal to, actually I am writing these two equations just to eliminate this K dash. Here I have written these two equations to eliminate this K. So PH2 divided by PH1 will be equal to V2 raised to power 1.6 divided by V1 raised to power 1.6 into F2 raised to power, F2 raised to power minus 0.6 divided by F1 raised to power this minus 0.6. PH2 will be equal to PH1 into V2 raised to power 1.6 divided by V1 raised to power 1.6 into F2 raised to power minus 0.6 divided by F1 raised to power minus 0.6. That is equal to PH1 is given as 340. This is 340 multiplied by V2 is 230, V1 is 220, whole raised power 1.6. We can write it as like this. So F2 is now 50 Hertz, F1 is 60 Hertz. It is 50 by 60 raised power, whole raised power minus 0.6. It comes out to be 407 watt, 0.25 watts. Total hysteresis, this should have been core loss, that is C. I don't know why I have exchanged them, but I want you to please correct it. So PC will be equal to this loss plus this loss is equal to 538.4. This is how we can calculate the eddy current losses and hysteresis losses at different voltage and frequency. I hope you understood this. Sometimes you can see that this Bmax here is proportional to 220 by 60. Here it is 230 by 50. Voltage is less as compared to this, frequency is more. Here voltage is more, frequency less. So Bmax has changed here. When Bmax has changed, it is convenient to use this type of the formula, because here we have eliminated the value of Bmax. Actually, this is used for each and every formula where this voltage and frequencies are given. But sometimes the question may be slightly different, like this we have. In a transformer, the core loss is found to be 52 watts. This is core loss, not hysteresis or any eddy current loss. At 40 Hertz and 90 watt at 60 Hertz. Both losses being measured at the same peak flux density. That means BM is same. Compute the hysteresis and eddy current loss at 50 Hertz. We need to find it at 50 Hertz. So we'll be using these formulas, that is this and this. Here this BM is constant, this BM is constant. So we will be using this formula. It becomes slightly convenient as compared to this because in this case voltages are not given. So when this is constant, this PE, let us say it is equal to uh, some constant into F square. That constant will be now both K into BM square. This pH will be some constant into F, which will be equal to this. This constant will be equal to KH into BM raised to power 1.6. So that's what here it has been written. So PC will be equal to KH, that's the hysteresis loss constant. F into BM raised by X, X will be equal to 1.6. So plus KE F square BM square. Since BM here is constant, it will be equal to some small KH into F, where small KH will be equal to KH into BM raised to power X. Similarly, for this case, this will be equal to KEF square, while KE is equal to KE into BM square. So this is the equation will become simpler. So now PC is given at two frequencies. At this frequency 40, at this frequency. Actually, this becomes now equation two variables. What are these two variables? KH and KE. We need to find out KH and KE from the first two equations, first two given values, because in first equation this is given, PC, F is given, and second equation new PC is given and new F is given. So we can use these two equations to calculate KH and KF. And finally at 50 Hertz we give the value of this. We already have calculated K and KC, KH and KE. We can find out PC. So that's what is the procedure for this. At 40 Hertz, 52 is equal to KH into 40 plus KE into 40 square. So at 60 Hertz, 90 is equal to KH, where this is the core loss, this is the frequency, KH into 60 plus KE into 60 square. So when you open it up and you calculate or solve for KH and KE, KH will be equal to 9 by 10 and KE will be equal to 1 by 100. So the hysteresis loss will be now KH into F, it will be equal to 9 by 10, that is this, into 50, that is 45 watts, and KEF square will be equal to 100 into 50 square, that will be 25 watts. So this is how you can calculate different types of you can calculate different core losses at different frequencies and voltages, but try to remember and try to identify which formula to use where. When this BM is kept constant, then you will use this type of formula. When it is not constant and voltages are given, you can use this type of formula. So but you should keep both the formulas in mind and try to identify the problem, and as per problem you can use which type of formula is suitable for you. Now coming to the transformer testing, usually transformer testing is done to first determine the polarity and then to determine its equivalent circuit. So when we test a transformer, there are actually two difficulties that occur while testing a transformer by using direct load test. The first being, when we use the load test, there will be a large amount of energy that has to be wasted in such a test, and it's very impossible for us to arrange such a large or enough load for the direct loading. It will be very difficult. Yes, in labs we may be able to load the transformer by having a loading of let's say 1 kV, 2 kV or up to 5 kV, but beyond that it's very difficult to arrange such loading. So to avoid that, we usually do the test for the transformer which are of non-loading tests. In these tests, the power consumption is simply that is needed to supply the losses only. So there will be again power loss in doing such tests, but they will be only minimum. They will be only this losses. So the two non-loading tests are the open circuit test and the short circuit test. In both the test voltages, in both the tests, voltage, current, and power are measured, and from these we can calculate resistance and reactance of the input impedance can be found, and it can be found whether referred to primary side or secondary side. Only 4 parameters can be determined which correspond to the approximate equivalent circuit. So before going into the open circuit and short circuit test, we first usually do the polarity test. And I have told you in the lab that polarity test is usually done for a transformer before connecting it as parallel or as delta in a three-phase system. So this is the polarity test. So this is the primary of the transformer where we supply it through some voltage, and the secondary we keep it open. So we short circuit these two terminals. Let's say it is called as A2 and this is called as capital A2, and we measure the voltage around this. In lab we have done the other way around. We actually short circuit this and we measure the voltage over here. So this is one and the same thing. So when we measure the voltage, if that voltage will be equal to V1 minus V2, so in that case you will see that this polarity and this polarity will be same, because when you use the KVL, V1, this is minus plus, let us say this is plus minus, and this is, let us say, plus minus. So minus plus take as plus, it will be V1 plus this V1 minus V2 minus V will be equal to 0. That means V will be equal to V1 minus V2. Similarly, for the other case, if this voltage measurement is equal to V1 plus V2, in that case this has to be the reverse. That means positive would have been here. So that means dot, if we have assumed dot to be here, other dot will be here when we have the measured voltage V1 plus V2. So when voltage is V1 minus V2, that means these 2 points have the same polarity. The dot can be plotted at this point. So it is immaterial whether you use dot here or here. We can use here dot also, because that means the polarity, whatever the polarity is here at that instant, same with the polarity over here. So that is immaterial. There is one more test which is using a DC test. We use a switch over here from the primary system, from the of the transformer, and a DC battery, and at the secondary we use the DC voltmeter. When the switch is open, during that transit, when the current increases, there will be some flux, that means changing flux, that will be linking to this. The voltmeter will show some deflection. If it shows the positive deflection in the right side of the direction, that means this is positive, this is negative, and the current is flowing in this direction, that means this will be positive and this will be negative. These two have the same polarity. So on closing the switch, if the direction of the pointer of this voltmeter is on the left side, that means the current is flowing from this side. This will be positive and this will be negative. That means dot will be this and this. These two will have the opposite polarity. So this is also a convenient test that is used for the transformer. So as I have told you earlier, that this test is usually done for before connecting the transformer in parallel or in delta for a three-phase system. So this was about the polarity test. Now coming to the open circuit test. The purpose of this test is determined to the shunt branch parameters of the equivalent circuit of the transformer, that is GI and this BM. So one of the winding is connected to the supply at rated voltage. This winding is connected to the supply at rated voltage, and another winding is kept open circuited. From the point of view of the convenience and availability of the supply, the test is usually performed on the low voltage side. That is, the supply is given on the low voltage side, and the high voltage side is kept open circuit. This is kept open circuit. So if the transformer is used at the voltage other than the rated, the test should be carried out at that voltage. That means if the transformer is not used in practical, or in some case it is not used in rated voltage, the test should be exactly carried out at that voltage, because there will be some difference in the parameters when the voltage that we supply to the transformer, if that changes. So the meter reading is arranged so that this voltage voltmeter V will read voltage. This ammeter A will measure the current I0, that is the no load current or exciting current, and power input to this will be measured by this wattmeter W. So one more thing that we need to be ready, because this will be the actual equivalent circuit which will be of this transformer upon this no load test. Indeed, the no load current I0 is so small, this current will be very small, that is 2 to 6% of the rated current, and R1, X1 are also small. The V1 can be regarded as even. So this V1 will be kept as same as even. That means we can simply neglect this resistance and inductance. Series impedance can be neglected. We can assume that V1 is as if it is applied to this parallel branch. So our equivalent circuit will become like this. So this means for our practical purpose, the power input on no load equals to the core loss, because this power input will be only consumed by the core loss component of this exciting branch. That means this P naught that is measured by this wattmeter will be equal to Pi, that is iron loss. Now from these readings, the shunt branch parameters can be easily calculated. So first Y naught, that is the admittance of this whole branch, that will be equal to this I naught divided by V1, which is equal to G1 minus JBM. That is, and from here we can calculate Y naught. So from this equation, V square into GI, V1 square into GI will be equal to P naught. That means GI will be equal to P naught divided by V square, V1 square. So when we calculate GI and this Y naught, so we can calculate BM. BM will be equal to square root of Y naught square minus GI square. So here we can calculate both the values. These values are referred to the low voltage side. Since we have given the supply to the low voltage side, they will be definitely referred to low voltage side, from which the test is conducted, and could easily be referred to other side. We can use them to refer to the other side by if we know the transformer ratio, by the inverse square of the transformer ratio. The transformation ratio, if it is not known, then it is very simple to do by giving supply to one side of the transformer and noting the voltage that you are applying on the transformer, and then you can measure the voltage at the secondary side. By doing this, you can calculate, or you can measure the transformer ratio of the transformer. One more important thing, the wattmeter used for this test should be low power factor wattmeter, because in this case you will see that the power factor of V and I, the power factor angle between V and I naught, is very small. So in that case, to have a proper reading of the wattmeter, the low power factor wattmeter should be needed, as this circuit will have low power factor. Now coming to the short circuit test, as the name suggested, we actually short circuit the secondary of the transformer. This test serves the purpose of determining the series parameter of the transformer. For convenience of the supply arrangement and the voltage and current to be handled, the test is usually conducted from the high voltage side of the transformer, while the low voltage circuit is short circuited. Low voltage winding is short circuited, as shown like this. As I have told you, for if this is high voltage side, this is low voltage side, you can see here when we short circuit it and we apply the voltage that is applied across this will be very small, up to 5 to 10%, to be that will be sufficient to make current to flow through this, which will be equal to the full load current. So when the supply voltage is very small, you will see that the exciting current will be also small, because for full load current, when giving the rated voltage, that will be around 2 to 5%. So for this much of the voltage, it will be only for 0.2 to 0.5%. You can change it, maybe 0.2 because of this 2%. It will be 0.2 to 0.5% only. So while doing that, it will be good practice, you can say accurate practice, to neglect the parallel branch while doing this test, because there will be negligible voltage drop that is produced by this current, and we can assume that the parallel branch as if it is not there, because it is not drawing that much of the current. So thus the shunt branch of the equivalent circuit can be altogether neglected, giving the equivalent circuit shown below. That the equivalent circuit will be now this one, because here there will be almost zero current that's flowing through this. That equivalent circuit will be, it is as if it is open circuited. Since the transformer is excited at very low voltage, the iron losses are negligible, because this will be only 2 to 10%, sorry, 5 to 10% voltage will be applied across the primary of across the high voltage. The core losses, which are dependent upon the voltage, they will be neglected. We can see whatever be the losses in this test they are only the copper losses. So that means PSC, that is the power that's consumed due to this short circuit test, will be the power consumed by the winding resistance. So this is our final approximate equivalent circuit during the short circuit. So now it is very easy. From the equivalent circuit, or the figure shown above, the circuit parameters are now computed below. Since from the measurement point of view, voltage is measured as VSC, current measured is ISC, power input is PSC. So when we get the ratio of VSC divided by ISC, we get total impedance, which is equal to square root of R1 plus R2 square plus X1 plus X2 square. So this R1 plus R2 can be calculated from the power input. This ISC square into R1 plus R2 will be equal to this PSC. From this, R1 plus R2 will be equal to PSC divided by ISC square. So that is given over here. So Z is equal to VSC by IC, which is equal to R square plus X square, where R is equal to combination of these two resistances, that's R equivalent, and X is equal to combination of these two reactances. So R is equal to PSC divided by IC square, that is the power loss will be only consumed in these two resistances. So R is equal to PSC by IC square. Similarly, X will be then equal to Z square minus R square. So we can calculate this X1 will be equal to, let us say it is referred to high voltage side, it will be equal to X1 plus X2 dash. Then you can calculate the X2 that we have already done in the lab. That will be then multiplying it by the inverse ratio of the transformer. Similarly, R2 dash can be also calculated. That is this R2 dash can be calculated by changing this transformer ratio. Then we can get the actual value of the R2. So it is observed that the SC test has given us the equivalent resistance and reactance of the transformer. It is not yielded any information for separating these two. That means we know that R1 plus R2, but we don't know the exact value of R1 and R2. But for simplicity, we take R1 is equal to R2 is equal to their half, that is R by 2. Similarly, we take this X1 is equal to X2 is equal to X divided by 2. Now it was observed that the open circuit test and short circuit test give us together give the parameters of approximate equivalent circuit, which as already pointed out is quite accurate for all important computations. So we usually use these types of the parameters to analyze the transformer for any purpose. Let us try to do one of the numericals. It will be quite then very simple to understand how to do this. The following data were obtained on a 20 kVA 50 Hz 2000 by 200 distribution transformer. We need to draw the approximate equivalent circuit of the transformer referred to high voltage side and low voltage side respectively. So the open circuit test uses the voltage that is measured 200, that's the rated voltage on low voltage side, that is current, that's no load current will be the 4 amperes, and the power will be 120 watts. So this power will be actually the iron losses. On short circuit test, the rated voltage that is given, will be 10 amperes. Since this is done on the high voltage side, you can calculate this to 20 kVA divided by 20,000 will be equal to 10. That means this will be the rated current. If we have done on this side, this would have been 100 amperes, which would have been very difficult to handle by the equipment that may be present in the lab. So that's why it is done on the high voltage side. So power measure will be 300 watts. So from open circuit test, this Y naught will be equal to I naught divided by V naught, that is equal to 4 divided by 200, that is 2 into 10 to the power minus 2. So GI will be equal to 120 divided by this 200 square, that is equal to 0.3 into 10 to the power minus 2. So Bm will be equal to square root of Y naught square minus G square. It is equal to 1.98 into 10 to the power minus 2 Siemens or more. From this we have calculated the shunt parameter. On the short circuit test, first we calculate Z. Z will be equal to this voltage divided by current, that will be equal to 60 divided by 10, that is 6 ohms. And this R can be calculated from the power. So that means 300 divided by this square will be equal to R. 300 divided by this current square will be equal to 3. So X will be equal to square root of 6 square minus 3 square, that is equal to 5.2 ohms. So transformer ratio from here, that will be equal to 2000 divided by 200, that is 10. So equivalent circuit referred to high voltage side. Since these two have been calculated on referring to the low voltage side, so we need to convert them to the high voltage side. So by dividing them, the transformer ratio, because here we have to be very careful while referring them to high voltage side. Usually the impedance are multiplied by the transformer ratio square, but here they have to be divided because they are admittance. So this is conductance, this is susceptance. So they will be divided by 10 square. It will be 0.3 into 10 to the power minus 4. So it will be 1.98 into 10 to the power minus 4. So high voltage side we have this because these two are calculated referred to high voltage side because we are giving supply to the high voltage side. So high voltage circuit parameters are this, and then parallel circuit this, and this will be the series circuit. Now low voltage circuit, we have the parallel circuit this, and we need to convert them into the low voltage values. So the equivalent circuit for the low voltage value is that we need to divide this R divided by 100 square, 10 square, that will be 0.03, and this x also divided by this 100 square, it will be 0.052. So this will be the circuit which is referred to the low voltage circuit, sorry, low voltage, because they are not to be converted, they are already calculated with respect to low voltage running, only these are to be transferred. So this is already this is the transformer circuit referred to high voltage side. These two have already been calculated while the transformer is supplied from the high voltage side, so we don't need to convert them. We need to convert them these values only which we have converted over here. So I think this is enough for today. Thank you.